For more than a century, water treatment has relied on physical barriers, filters, sandbeds, and membranes that separate particles based on size. But the smallest contaminants, including nanoplastics, dissolved chemicals, and emerging pollutants, exist at a scale where traditional filtration reaches its limits. To remove them, environmental engineering is entering a new dimension, the nano. At this level, materials are no longer passive barriers. They become active, selective, and highly efficient separation systems. And for the first time, these technologies are moving from large treatment plants into our homes. A nanomaterial is defined not just by its size, but by its structure. At dimensions below 100 nanometers, materials behave differently. Surface area increases dramatically. Chemical reactivity changes. Electrical properties can be controlled. This allows engineers to design membranes and adsorption media that interact with contaminants at the molecular level. Instead of simply blocking particles, these materials can attract, repel, or transform them. This is a fundamental shift from mechanical filtration to engineered separation. One of the most promising nanomaterials for water treatment is graphene, a single layer of carbon atoms arranged in a hexagonal lattice. When nanopores are introduced into this structure, graphene becomes an ultra-thin membrane with extraordinary properties. Water molecules pass through rapidly. Larger molecules and particles are rejected. Because the membrane is only 1 atom thick, resistance to flow is extremely low, which means lower energy consumption. For point-of-use systems, this could redefine the balance between performance and efficiency. Not all nanomaterials act as membranes. Some function as advanced adsorption media, nanostructured activated carbon metal-organic frameworks, and functionalized polymers create enormous internal surface areas. Contaminants attach to these surfaces through van der Waals forces, electrostatic attraction, chemical bonding. This allows compact filters to remove pollutants that would otherwise require large-scale treatment processes. For households, this means higher performance in smaller devices. Water quality is not only about particles and chemicals. Microbiological safety is equally critical. Certain nanomaterials, such as silver nanoparticles and photocatalytic titanium dioxide, have antimicrobial properties. They prevent bacterial growth on filter surfaces and reduce biofilm formation. This extends filter lifespan and maintains consistent performance. Instead of periodic disinfection, the material itself becomes a protective mechanism. What makes nanotechnology transformative is not only its performance, but its scalability. These materials are now being integrated into point-of-use systems that fit beneath a kitchen sink. Multi-stage cartridges combine nanomembranes, nano-adsorbents, antimicrobial layers. Each stage targets a different class of contaminants. The result is treatment performance that once required an entire municipal facility, now operating at the scale of a household. Introducing nanomaterials into drinking water systems requires strict safety control. The materials must remain stable and fixed within the filter matrix. They must not be released into the treated water. Environmental engineering addresses this through encapsulation, structural bonding, and certification testing. Performance is not enough. Long-term material integrity and public health protection define successful implementation. The next step is the combination of nanomaterials with digital monitoring. Smart filters will not only remove contaminants, but they will measure performance in real time, predict replacement intervals, adapt flow conditions for optimal treatment. Filtration becomes a responsive system rather than a passive device. And clean drinking water becomes a continuously verified resource. At the nanoscale, materials are no longer just filters. They are precision tools for protecting human health.